Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the root and the ratio test. Let us recall what we've done so far. So we have defined what is a series. A series is just, as a symbol, it's just any expression of this sort where ANs are natural numbers, ANs are real numbers. And once we have any such series given, then we can define sequence of partial sums. So the nth partial sum of the above series is given by this sum. This is an actual real number. And then once we have these two definitions, then we can define what it means for a series to converge. So we say that a series is convergent if the sequence of partial sums converge to something. And we say it's divergent if the sequence of partial sums diverges. Once the sequence of partial sums converge, meaning if the series is convergent, then we call the sum of the series as the limit of the sequence of partial sums. So if this limit exists, then we call it the sum of the given series. And we saw a criterion that if you have a convergent series, then the sequence of summands, meaning the ANs, that better converge to 0. That's a necessary condition for a convergent series. We also saw the Cauchy's criterion that if we have that above series, then this kind of thing where you take k equals m, let's say m plus 1 to n, a k. So this thing becomes arbitrarily small as you have m and n greater than or equal to some large enough n. So what it says that for all epsilon greater than 0, there is some natural number n such that whenever m and n are greater than that natural number, this thing is less than epsilon. So that's the if and only if condition for a series to converge. And that follows simply because you apply the Cauchy criterion for convergence to the sequence of partial sums. So this is not a deep result. And then finally we saw in the last lecture the algebra of convergence, where if you have, let's say, two convergent series, then their sum also converges and scaling also converges and stuff like that. So that's what we've done so far, and now let's proceed to today's material. Here are the problems. So this is the first problem, and then this is the second problem. Okay, so now we start with today's material. So first thing we are going to do is something very simple. It's called the comparison test. So what we have is we have two sequences of real numbers such that this kind of inequality happens, and then we want to show that if the series formed by the second sequence converges, then so does the series formed by the first sequence. So it's not surprising at all, but let's give a proof, and proof is just one line use of Cauchy criterion. So fix some natural number n, then this summation let me write a plus 1. This thing is obviously at most by triangle inequality more absolute value of ak, which is at most bk. So okay, so don't fix any capital N. Let for all m less than n, m greater than or equal to 1, we have this very simple inequality. And now if both m and n, or I should just say that if m is exceeding some natural number n, where n is if n is chosen large enough, then this can be made arbitrarily small. That is the Cauchy criterion for convergence applied to the second series. So this can be made arbitrarily small if m is chosen large enough, and therefore this can also be made arbitrarily small if m is chosen large enough. And therefore by Cauchy criterion, this thing converges. So it's a very simple result. And a slight generalization of the above is the following. So this time what we have is we have two sequences of real numbers such that the same comparison happens, but this time we say that the comparison happens for all large enough n. So it is not happening everywhere, unlike in the previous thing. In the previous thing we said that it happens for all n, but now we demand that it happens only for some bigger, some large enough n. And the conclusion is the same. And this shouldn't be surprising at all. And I leave this as an exercise. Basically, if you have a series and to determine whether or not it converges, you just need to decide if its tail is convergent, meaning you can just throw away some first few terms and it doesn't alter the convergence-ness of that series. So all we can do is we can just throw away the first n terms and then use the previous thing and you'll get this. So there's nothing to do here. So these are called the comparison tests. Both are called the comparison tests. Anyway, the second one is the more general. Alright, so now for the interesting part. So this time what we have is we have a series of real numbers and we define this strange looking quantity. You take the absolute value of the nth part, then take the nth root of it, and then take the lim sup. So this could be infinite. This is not necessarily a real number, this could be infinite. And we define alpha as this lim sup. And here is the very interesting proposition is that if this thing is less than 1, then the series converges. If that thing is greater than 1, then the series diverges. And if unfortunately that thing turns out to be equal to 1, then we can't say anything. Okay, so we'll just do the, okay, I think we'll do the both directions, but let's see. So fine, so let's prove 1. Proof of 1. So we have alpha less than 1. Then if we unravel the definition of lim sup, then for any beta, so let beta be such that alpha is less than beta is less than 1. And now using the definition of lim sup, there is some n some capital N such that this quantity over which the lim sup was operated is less than beta for all n greater than equal to n. So all we are saying is that this must happen ultimately. Otherwise this lim sup will not be equal to alpha. So it's just this much is a very simple inference from the definition of lim sup. So what does this mean? This implies that the absolute value of an is less than beta to the n for all large enough n. Okay, and now since beta is in this range, we have this series converges. Why is that? Because this is the geometric series that we discussed in the previous lecture. It's a geometric series. And geometric series converge if the thing that we are using to exponentiate has absolute value strictly less than 1, which is happening in this case. So that thing converges, and therefore now by comparison test, but the second version of the comparison test that we just discussed, we have this series also converges. Okay, so that proves 1. Now let's prove 2. So assume alpha greater than 1. And And again, since we will exploit the definition of lim sup, since this lim sup is alpha, there is a subsequence of an such that this subsequential limit is alpha. So therefore, this guy is greater than 1 for infinitely many values of k. Right, since alpha is greater than 1 and this thing converges to something greater than 1, this thing should eventually become greater than 1. And that's what we've written. So for infinitely many values of k, this thing is, or I could just say ultimately for k, that's better. So this is ultimately over k, meaning for all large enough k's, that is, this inequality happens. And thus, this thing, okay, so which implies that this guy is greater than 1 ultimately over k, and therefore this sequence does not converge to 0 as k approaches infinity, which implies the original sequence does not converge to 0 as n approaches infinity, which implies that this thing does not converge. Because one of the necessary conditions for a series to converge is that the summands converge to 0. So that's it, that proves 2. And when alpha equals 1, then there are examples where the series converges and there are examples where series does not converge. So both can happen, and so it's inconclusive. Alright, so it's a very convenient and very useful test. It's just a matter of finding this lim sup, and let's take one example when that kind of thing appears. So it's a very, it's an example which I could have taken long ago, nothing to do with this lecture, but it's just for some practice. So we claim that this thing converges to 1 as n converges to, n approaches infinity. So this is the claim that we'll prove. So here is the proof. So since n greater than or equal to 1, we have this guy is equal to this for some delta n greater than 0. What are we saying? We are saying that this is greater than 1. That's all we are saying. So for n greater than or equal to 1, this is definitely greater than 1. And therefore, we have that. And thus, 1 plus delta to the power n is same as n. Let me write it better. So thus n is equal to 1 plus delta n to the power n. And here we'll use the binomial theorem, which we are familiar from high school. And so on. Okay, we have that. So therefore, in particular, n is exceeding the second term. It's a bunch of it's equal to the sum of a lot of non-negative things. So it will be greater than equal to any of the summands that appear on the right hand side. In particular, it's greater than equal to the third summand, which is n choose 2 delta n square, which is nothing but n into n minus 1 by 2 delta n square. Alright, which implies 0 is less than equals to delta n less than equal to 2 by n plus 1 square root. Sorry, n minus 1, I think, yeah. So all we did was we just used this and did the algebra. Okay, so we have that, and that implies, this sandwich implies that limit, this is 0, which implies limit equals 1, because the limit of this as n goes to infinity is just equal to 1 because that guy gets killed. So that's a very nice example to see in action. Okay, and now for the other very nice test, which is the ratio test. So this time what we have is, again, we have a series, and assume that none of the terms are 0. Then this series converges if this lim sup is dominated by 1 strictly, and diverges if something else, there's nothing to do with the original lim sup, but something else happens ultimately. So these are just two sufficient conditions. One sufficient condition guarantees the convergence, and another sufficient condition guarantees divergence. Okay, so let's prove both of them. Proof of 1. So let lim sup of this ratio be equal to something called alpha, and let's say this is less than 1. And we want to show that the series converges. Okay, so let beta be such that zero is less than beta is less than alpha. What have I written? Such that alpha is less than beta is less than 1. So alpha is strictly less than 1. So we've just chosen some beta between alpha and 1. Okay, so if we unravel the definition of lim sup, then we have this guy is less than beta ultimately. Which means what? Which means that there is some capital N large enough such that whenever little n exceeds capital N, we have that. Therefore, okay, so I think it's better to use an index. Fine. So let me modify this, or rather expand on that. Thus, there is some n greater than equal to 1 such that for all n exceeding capital N. So we have that. So therefore, if we substitute little n equals capital N in the above, we see an plus 1 is less than beta mod an, and mod an plus 2 less than beta mod an plus 1, and so on. Let me write one more guy. Sorry, this is incorrect. This is a capital N, capital N, capital N. And let's say we go up to k terms. So an plus k less than beta an plus k minus 1. Okay. Uh, yeah. So this is for all k greater than equal to, I think, 1 or maybe 2, it doesn't matter. Therefore, if we multiply all these inequalities, and it is legitimate to multiply all these inequalities because everything here is non-negative, so you can multiply all the inequalities, and since this telescopes, this cancels out with that, this with that, this with that, this, sorry, so once again, this cancels out with that, this with that, this with that, and dot dot dot, this with that. So what we get is this absolute value is at most beta to the power k. There are a total of k inequalities times mod an. This is for all k greater than equal to 1. Okay. So therefore, the series let me use another index. It's better in this, the way we have done things. K equals 1 to infinite, an plus k converges. So why is that? So we have this series and we have this comparison where this series, if we take this series, this series converges. This is because we have just scaled a geometric series, a convergent geometric series, because beta is less than 1 with some real number. So this thing converges, and now using the comparison test, this thing converges, which implies actually that the full original series, which was written this way, converges. Because as we remarked, if we have a series, then its convergence is decided or unaltered by throwing away the first few terms. So if the truncated series converges, then the original series converges, and if the truncated series diverges, then the original series diverges. So that's what we have done. So if this tail part converges, then the original thing also converges. Okay, so very simple proof, but it's a very useful criterion. So that's the proof of 1. Now let us do the proof of 2. 2 is very simple. So if this happens, an plus 1, okay, so if this ratio is greater than equal to 1 ultimately, then this is greater than equal to an for all n large enough. So for large enough n, which implies actually that ak is greater than, okay, so basically the implication is that this convergence does not happen. This does not converge to 0 as n goes to infinity. So let me just say why is that. So this happens for all large enough n. So you fix some capital N where, so what we'll see is a capital N plus 1 is greater than equal to a capital N, and by the same token this will happen, and then this will happen. So we see that this series cannot converge to 0 because it is dominating some non-negative thing. We have already assumed that these guys are non-zero, otherwise anyway all of these quantities don't make any sense. So that's the reason why this thing does not converge to 0, and therefore the divergence happens. So therefore this guy diverges. That's it. So these two tests are very useful, the root and the ratio test. And this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.